All right, so last issue. Quick reminder about what we talked about on Friday. So remember we were talking about on Friday, we were talking about how we could, we got the factor theorem, right? How we know that a factor, if k is a zero of a function, k is some number that's a zero of the function, right? So when I evaluate the function at k, I get 0 back, right? Which means if I use synthetic division, if I put the number k out in front, I get 0 in the remainder box, right? If that's true, then it just reminded us that we have this relationship. If k is a 0, then x minus k is a factor of the polynomial, okay? And we did some things last week where, if we could determine if 5 is a 0 of the function. If x minus 5 is a factor, then 5 would be a 0, and we would just check synthetically, and if I get a 0 in the remainder box, bingo. Okay. Then 5 is a 0, and x minus 5 is a factor. And we were able to use that to our advantage. We were able to use that to our advantage, like if we wanted to factor this thing. If I get a 0 in the remainder box, then I know that x minus 5 is a factor, and I just have to factor the rest of it, right? The rest of what's left over to completely factor the polynomial. Or more typically, we did problems like this, where if they gave me one 0 of -8, I found the other ones, right? I divided that through synthetically, and whatever I got left over, I turned that into a polynomial that I set equal to 0 to find the other zeros, right? So -8 was a 0, which left us with the polynomial 64x cubed plus 27. I have to find the zeros of that. Well, we ended up factoring that as a sum of cubes pattern, right? And we found out what the zeros were, right? Okay? So we did a bunch of that stuff. That's the hardest stuff we'll do in Unit 5 right there. Okay? From there, it's all kind of downhill, okay? The last thing we did was something much easier. We were going to reverse the whole story, and I told you I'm going to give you the zeros of a polynomial, and I want you to come up with the simplest polynomial that has those zeros. Piece of cake. All that means is we're going to convert each of the zeros into a corresponding factor, and the polynomial is just a product of those factors, right? So if 5 is a 0, then x minus 5 is a factor. If -6 is a 0, then x minus -6 or x plus 6 is a factor, etc., right? So we convert each of the zeros into a factor. We just take the product of those factors and expand all that out by multiplying through those little factors and creating a big polynomial. That's it. Easy, right? You have to be careful because you're doing some multiplication here, but it's really not a hard process, right? Okay, where we left off, though, was with a couple of little bit trickier problems, right? So we had to do a little bit of detective work here. If they gave us the two zeros, x equals 7 and x equals 2i, right? Well, we know how to convert those into zeros. If 7 is a 0, or in factors, if 7 is a 0, then x minus 7 is a factor. If 2i is a 0, then x minus 2i is a factor. But we had to account for something. We had to account for something we talked about a while ago, and that is that zeros, complex zeros with i's in them, always come in complex conjugate pairs. They come in twos, right? And so we know that if 2i, which is the same thing if I write it as a complex number in standard form, with a real part plus an imaginary part, we would say 0 plus 2i. Now we don't need the 0. Hey, William, I need your attention up here, please. Thank you. All right. So 0 plus 2i would be the complex number, if I wrote it out, has to go with its complex conjugate, which would be 0 minus 2i, right? But we don't need the 0 on there, but we need the minus 2i part. Those have to go together. They come in as a package. So when I include this other missing 0, then that gives me a third factor. X minus -2i is x plus 2i. I get the product of these three factors. At first that seems like, oh man, it makes it harder. No, it makes it way easier, way easier. Because when I multiply out these complex conjugate factors, look, I get x minus 2i times x plus 2i. And that looks like x plus or minus 2i, doesn't it, kind of? Right? By multiplying these complex conjugates together, I always get a really good, simple result when I do that.
So how do you get x squared minus 1?
Oh, okay, that's what I'm talking about. Okay, right
Don't
here.
the i's cancel?
So, right, exactly. When I multiply out complex conjugates, so a plus bi times a minus bi, where a and b could be anything, right? But we're going to follow this pattern. We always get the result a squared plus b squared. Right? The i's go, okay? So if we back up one slide here, well, here I've got a minus bi times a plus bi, so I get a squared plus b squared, x squared plus 4 squared, right? Or x squared plus 2 squared, sorry, x squared plus 4. And then all I have to do is multiply that by x minus 7, so I distribute the x, I distribute the negative 7, add like terms, drop the pen, we're done, right? Escape, okay? So there's, you're going to see just a couple like that on the very last assignment, 5.7 practice 2. Okay. What about one like this? Okay, here's another one. We got to be a little bit careful with it. So this time they're giving us the zeros x equals 1 or x equals negative radical 10. Okay, so we can build factors. If 1 is a 0, x minus 1 is a factor. If negative radical 10 is a 0, x minus negative radical 10, which is x plus radical 10, is the factor. Okay, but look what would happen if I were just to stop there and I were to multiply out, FOIL out those two binomials. Am I going to get square roots in my answer? No. I'm not? If I just took those two white factors, x minus 1 times x plus the square root of 10, right? I'm going to get square roots in my answer, aren't I? Agree?
Yes.
Okay, I don't want them. The directions say we want to write a polynomial function of least degree that has integer coefficients. I don't want any square roots to be multiplied by my x's, my powers of x, right? So if that's the case, if my polynomial is going to have rational coefficients, which are coefficients that can be written as fractions with no square roots, and I want integer coefficients, I want even better than that, right? Then I have to somehow get rid of that square root of 10. Well, here's the recipe for that. It's the irrational root theorem. It tells us that if a polynomial has rational coefficients, then any irrational zero has to come with a conjugate partner so they can cancel out when I multiply the factors.
So
right?
it's the same thing with the i's.
It's exactly the same thing,
Is
except
that the word
without i's.
conjugate?
Say it again.
Is that the word conjugate pairs? Is that what
That conjugate pairs, yep, conjugate pairs. And if we have an I in there, we call them complex conjugates because they have i's in there. But if they don't have an I, we just call them conjugates. They're not complex, they're just conjugates. So in this case, we've got, they gave us the 0, x equals negative radical 10, which is the same thing as 0 minus radical 10, right? If I want to get rid of the square roots, I have to include its partner 0, which would be x plus radical, or 0 plus radical 10. I don't need the 0, but I need the plus radical 10 part, right? So if I create a third factor then, corresponding to this other 0 that's a conjugate partner with the negative radical 10, I get x minus radical 10 times x plus radical 10. That's good. That's going to make things simple because that also follows our pattern. If I have regular conjugates, not complex conjugates, a plus b times a minus b, as we've known for a while, just equals a squared minus b squared, right? So in this case, I've got x plus radical 10 times x minus radical 10. Well, that fits my pattern of a plus b times a minus b. So I'm going to get x squared minus the square root of 10 squared. Well, what's the square root of 10 squared? Thank you. Is 10, right? So I'm going to get x squared minus 10 coming from that product. The square roots went away. Perfect. That's what we wanted, right? So then all I have to do is multiply x minus 1 times this x squared minus 10. Just distribute the x, distribute the negative 1, add like terms, drop the pen, we're done, right? Okay. So there you have it. Okay, now last issue. What happens, we started kind of talking through about how, we could come up with a way, if I don't get any hints, how could I solve, find the zeros of a polynomial, okay? And we led up to something called the rational root theorem, okay? And it's going to allow us to solve problems like this one. This is the problem we're going to do as a group today. And then, when we're done with this, you're going to have plenty of time. I want you to go into the very last assignment, 5.7 practice 2, and I want you to try one of the problems in the last group, in the rational root theorem group of problems. I want you just to show me that you can do one of those today. And then after that, you can work on anything you want to. I gotta see with my own eyes that you can do this stuff first. Okay, we gotta nail this down today, and then you've got the rest of the year to just finish stuff up. Okay, but here's the kind of problem we're talking about. Find all the real zeros of this polynomial. Okay, it's a third degree polynomial, it's got 4 terms. So what would our strategy be for trying to factor that thing? Are we gonna do, I mean, you know, if we got 2 terms, we use factoring patterns. 3 terms, we just use magic numbers, we use quadratic trinomial patterns. We split it into groups. Good, very good. We group it. Okay, but that's great. That's our strategy. But factoring by grouping is sadly not going to work here. I can tell you it's not going to work. You can predict it's not going to work if you look at the coefficients. It's a great idea, though. That's what we should do. We should at least think about it. Look at the coefficients. My first 2 terms, I get a 2 and a 3. My second group of 2 terms, I get a -9 and a -10. We can already tell that those are different ratios, and so it's not going to work. 2 divided by 3 is different than -9 divided by -10, so grouping's going to fail. Don't even try. It was the right thing to think about, though. It's the only thing that we currently would have any hope of doing. But today we're going to come up with a way to maybe get out of this dilemma, okay? And it's called the rational root theorem. Now let me summarize this. The notes are already up. They're already online for today. So you can already go back and look at this when you need to. And I've got a PDF up there from a textbook if you want to read about it. But let me summarize it for you. It's really not that hard. The rational root theorem says that all rational zeros, which would be any zero that can be written as a fraction, has to be built in this way. The fractions that you get for those zeros. And by the way, is 7 a fraction? The number 7? It is technically. What's on the bottom? 1. Okay, so we can think of that as a rational number 2. That's a fraction 2 with a 1 on the bottom. So all rational zeros of any polynomial always are built from the numerator is going to consist of a factor of the constant in the polynomial, and the denominator is going to be a factor of the leading coefficient every time, right? Always works that way. And we looked at a couple examples last week at the end of the week where if we found that the polynomial that I build from these rational zeros, x equals 5 halves, -6 halves, and 10 ninths, the simplest one we can build ends up having a 90 as my leading coefficient and a 300 as my constant. It's not an accident that 5 and 6 and 10 are factors of 300, and 2 and 5 and 9 are factors of 90. It will always be that way, every time. If you have a rational zero, the numerator is going to be a factor of the constant, and the denominator will always be a factor of the leading coefficient, every time. Okay? So we can use that to our benefit then, for a problem like this. Okay? So, say it again. Well, okay, so the leading coefficient is 2, right? What are the factors of 2?
1 and 2.
1 and 2. So we know that if we have rational zeros of this function, the denominator has to either be a 1 or a 2. Okay, guaranteed. Okay. The numerator has to be a factor of the constant, which is 10. Well, what are the factors of 10?
2 and 5.
Well, 1, 2, 5, and 10. Okay? So then let's make a list. The way we're going to do this is we're just going to make a list of possible zeros, and we're going to try them all until we get one that works. Okay? That's it. So the first part of our list, let's assume that the denominator
2
equals 1. Okay, we'll start with the easiest ones, right? Denominator of 1 makes easier fractions than the denominator of 2, right? So if we make a list of possible zeros, we'll start off with the denominator of 1. So what are the factors of 10 again? 1, 2, 5, and 10. So the possible zeros would be 1 divided, plus or minus, it could be positive or negative. 1 divided by 1, which is 1, plus or minus 2 divided by 1, so plus or minus 2, plus or minus 5 divided by 1, or plus or minus, what's bad plus or minus? plus or minus 10 divided by 1. Okay, for part 2 of our list, let's assume that the denominator equals 2, the other possibility. Okay, so then we'd have to add plus or minus 1 divided by 2, right? Plus or minus 2 divided by 2, but what's that? 1. I've already got that on the list, so I can ignore that one, right? Plus or minus 5 divided by 2, or plus or minus 10 divided by 2, but what's that? 10 divided by 2 is 5. It's already on the list, right? So we've only got 2, 4, 6, 8, 10, 12 possible zeros to try. Okay, now here's the deal. I'm going to make you a deal. We're getting down to the end of the wire here, right? So we don't really have time, and I don't want to bog your already overburdened brains that are in much need of probably a little bit of a rest from all this stuff, right, over the summer. Okay. I'm not going to burden you with any zeros that have denominators other than 1. There's always going to be, in other words, there's always going to be at least one zero that's not going to have a fractional, it's not going to be a fractional zero, it'll be an integer 0. Right? So you're always going to be able to just start at the easy end of the list and work your way through the list, and before you get to the fractions, you'll find a hit. You'll find one that gives you a 0. Okay? But I want you to get used to the process. That's the main thing. Okay? So here's the way we can do this as a process. The easiest way to test if a number is a 0 is to use synthetic division, right? We just want to see if there's a 0 in the remainder box. But it's a real pain to have to redraw that synthetic bracket time and time again and always write in all the coefficients, right? That's a lot of extra writing. So I'm going to show you a shortcut way of trying lots of zeros in a row that's very efficient. Okay, it's called tabular synthetic integration. But here's how it looks. You draw a horizontal line and you draw a vertical line that represents the front of the bracket. Okay, so then the coefficients just go, you know, they go inside the bracket, right? So our coefficients would be 2, 3, -9, and then there's going to be another vertical line that represents the remainder box. And so the one number that would go above the remainder box would have been the -10 in synthetic division, correct? Right? Okay, now we pick values. We're going to try some values out front. So let's start off with +1, how about? Okay, so if I try +1, now here's the way this works. We're going to do a little bit of math in our heads. So we're only going to write down the numbers that show up underneath the synthetic bracket, right? So imagine we're doing synthetic division. We would drop the 2 all the way down below the bracket, right? And then what do we do? Then we multiply by the 1 out front. So 2 times 1 is 2. But instead of writing the 2 down, we're just going to go ahead and add it directly to the 3. So 2 plus 3 is 5. Okay, so the next number below is a 5. 5 times 1 is 5. Plus -9 is -4. -4 times 1 is -4 plus -10 is -14. I did not get a 0. So that one failed. So we can cross +1 off of the list. Okay, see how that works? And then we'd move on to another one. Now I'm going to purposely pick one that doesn't work here just so you can see, maybe you can see like one additional failure, right? So what if we pick +5? Okay. If I pick +5, I'd bring down the 2. 5 times 2 is 10 plus 3 is 13. 5 times 13, I'm already getting pretty big numbers. This isn't going to work, is it? You can already predict. This gives me 65 plus -9 is 56, way too big. It's not going to work. So we could cross +5 off the list.
Let's try that too.
Let's try that too and just see what happens with
Just
that
see
too.
what happens.
So if I pick 2, okay, I drop the 2 down. 2 times 2 is 4 plus 3 is 7. 2 times 7 is 14 plus -9. 5. 2 times 5 is 10 plus -10 is
We've done something, Mr. Loya.
0. We have done something. We do lots of things in here. We just did something kind of good. So we know that 2 is a 0, right? So we can put that in our answer box. We know that one solution is 2. We got to keep going. Okay? Well, to keep going, from here on out, that was like the log that broke through the log jam, and now it gets really easy, right? Because once we found that 1, 0, what's left over when we divide through by the factor x minus 2 is this other polynomial right here, right? Well, if this is the remainder, this is the constant, that's the coefficient of x, and that's the coefficient of x squared, right? So we're left over with, if we divide the original polynomial f of x by x minus 2, we get 2x squared plus 7x plus 5, and our goal is to find the zeros of that. But that's quadratic. That's easy, right? That's Unit 2 stuff. We can do that, okay? I mean, we're up here in Unit 5. Let's go back in Unit 2, right? So we can solve this quadratic equation any way we choose to. We can't isolate x. We could factor this using bottoms up or grouping if you really want to be tricky. But probably what do we do if I can't divide both sides by a number to make it easier and I'm stuck with the number out in front of the x squared? Probably just quadratic formulas, right? So if we solve this, we're going to get x equals negative b, so negative 7, plus or minus the square root of b squared. Is everybody with me here? What's b squared? 49. Minus, now I've got to do 4 times a times c, right? So we always want to try to multiply those in a smart order. Well, I would do it this way. 2 times 5 is 10. Times 4 is 40. So 49 minus 40 under the radical, and it's all divided by 2a, which is 4, right? Okay, so what's that give us then? That's going to give me negative 7/4 plus or minus square root of
3. Well, no, just 3.
Okay, square root of 9 is 3, good. Plus or minus 3/4 if I split my common denominator. And so now I can find my solutions pretty easy. If I take the plus sign, what's x equal to? What's negative 7/4 plus 3/4?
Negative 1.
Negative 4/4, which is negative 1, right? So there's one answer. X equals negative 1. There's another 0 we got. Okay, what if we take the minus sign? I get negative 7/4 minus 3/4. What's negative 7/4 minus 3/4? What is that? Negative 7/4 minus 3/4 is negative. Okay, new problem. What's 2/5 plus 1/5? 3/5. I get a common denominator. So what's negative 7/4 minus 3/4? Negative 10/4.
And you know what I said? I said 5 2s.
Ah.
You all laughed at me.
Which was you were very close. It's negative 10/4, which is very close to 5/2, but it's negative 5/2.
It was implied.
Oh, it wasn't implied. So we get x equals negative 5/2 and x equals negative 1. So we could just add those to our list, and that's all of our zeros. Okay, make sense?
Yes.
You got this stuff, right? Okay, I'm done. Go. I want to see you get through one of the problems in the last group of the last assignment, and then you're good to go on your own. Okay? Stephanie, this is for you. There you go.
Stephanie's in trouble.
Yeah, right.
You need God's attention.
Oh, there you go. There you go.